Hello, today we will study Chapter 14, Simple Linear Regression Model Part 1, the model. We will start with the population model. The simple linear regression model for the population has the form y equal to beta 0 plus beta 1x plus epsilon, where beta 0 and beta 1 are the population parameters. Moreover, beta 0 is the y-intercept or true y-intercept, beta 1 is the slope or the true slope, and epsilon is the random error in y. We want to study a linear relationship between x and y for the population model, so we take the expected value of y to get rid of this epsilon. There's expected value of y equal to beta 0 plus beta 1x. And we have three cases of the linear relationship between x and y. And case number 1, if this beta 1, the slope, is positive, then we have a linear relationship between x and y, which is positive linear relationship. In this case, the regression line is increasing or rising. Case number 2, beta 1 is negative, and we have a negative linear relationship between x and y, and the regression line is falling or decreasing. Case number 3, beta 1 is 0. There is no linear relationship between x and y. Now, for the sample model, this is the simple linear regression model for the sample. We start with the scatter diagram, or we call that scatter plot. Given paired observations x, y, y, I, x, I, y, I, a scatter diagram uses the x and y axis to represent the data. In this case, I equal to 1 all the way to little n. And this is what a scatter diagram will look like. And we use R, correlation coefficient, to measure the strength of the linear relationship between x and y by this equation, R equal to sum I equal to 1 to n of xi minus s bar times yi minus y bar for the numerator, and denominator is square root of sum I equal to 1 of xi minus x bar square times the sum of I equal to 1 to n of yi minus y bar square. And we study this equation in chapter 3. For chapter 4, we want to fit a line going through all our data. This is going to be called regression line, regression equation. As what we had mentioned, we want to find the relationship between x and y by fitting a line to the data set. And this is equation 14.4, estimated simple regression equation. Y hat equal to b0 plus b1x. Or for each observation, yi hat equal to b0 plus b1xi, where y hat is the dependent variable or response. Yi hat also is called predicted value for each of the observation. Yi is the actual value for each of the observation, and this ei is the error term, which is equal to the actual value minus the predicted value for each of the observation, and we also call that residual. Let us look at the linear regression equation further. At each observation, this y I hat equal to b0 plus b1 xi, where b0 and b1 are regression coefficients, and b0 is the y-intercept, which is the average value of y when x equal to 0, and b1 is the slope. And this, again, y I hat is the predicted value of y for each observation, and xi is the value of x for observation I. Next, we want to see how to find b0 and b1. We use the so-called least square method to compute b0 and b1. In this case, we minimize the error term square. So we have this yi is the actual value, this is the predicted value, and you have yi minus yi hat square, and take the sum, and then we minimize this sum of the error term. This is what we call the least square method. Using differential calculus, we can obtain the following results for the calculation of b1 and b0. The equation 14.6, the slope b1 is equal to the sum of xi minus x bar times yi minus y bar. For the numerator and denominator is the sum of xi minus x bar square. And equation 14.7, the y-intercept is b0 equals to y bar minus b1 times x bar. And we will set up a table to find this b1 and then find b0. Now, let's see an example. Given a set of data with n equals to 5, and we need to do the following. Develop a scatter diagram and approximate the relationship between x and y by drawing a straight line through the data. B. Compute b0 and b1. C. Interpret the regression equation and predict the average value of y when x equals to 5. And the set of data is as follows. x1 equals to 1, y1 equals to 3, x2 equals to 2, y2 equal to 7, x3 equal to 3, y3 equal to 5, x4 equals to 4, y4 equals to 11, and x5 equals to 5, y5 equals to 14. Now, here's the scatter plot. We have this xy coordinate system, and then we have those 5 data points. And now, when you draw a line going through all the data points, we have this y hat equal to b0 plus b1x, and you can see the slope is positive, and we have a strong positive linear relationship between x and y. Now, next, we need to compute b0 and b1. By doing so, we first compute the mean of variable x and the mean for the variable y. So you have 1 plus 2 plus 3 plus 4 plus 5 over 5 to get x bar, or the average for x is 3. And then we add 3 plus 7 plus 5 plus 11 plus 14 to get the numerator over 5 to get 8. Now, recall this equation 14.6, we have b1 equal to sum of xi minus x bar times yi minus y bar for the numerator, and the denominator is the sum of xi minus x bar square. So we set up a table to find xi minus x bar, yi minus y bar, xi minus x bar square, and also xi minus x bar times yi minus y bar. So you have for x1 is 1, so you have 1 minus 3 equal to negative 2, and then you have x2 equals to 2, so you have 2 minus 3 equal to negative 1, and then you have 3 minus 3 is 0, and 4 minus 3 is 1, 5 minus 3 is 2. That's for xi minus x bar, and for yi minus y bar, we have 3 minus 8 equals to negative 5, and 7 minus 8 equals to negative 1, 5 minus 8 equals to negative 3, 11 minus 8 equals to 3, 14 minus 8 equals to 6, and then we compute xi minus x bar square, which is negative 2 square equals to 4, minus 1, negative 1 square equals to 1, 0, 1, and 2 square equals to 4. We also need to compute xi minus x bar times yi minus y bar, which is negative 2 times negative 5 equals to 10, negative 1 times negative 1 equals to 1, 0 times 3 equals to 0, 1 times 3 equals to 3, 2 times 6 equals to 12, and that's xi minus x bar times yi minus y bar. This b1 equal to 26, so you add them up, so this is 26 over 10 equals to 2.6, and b0 equals to y bar minus b1 x bar. This is equation 14.7, and this is equal to 8 minus 2.6 times 3, which is 0.2. Now C, interpret the regression equation and predict the average value of y when x equals to 5. So we have our regression equation to be y hat equal to b0 plus b1x, which is 0.2 plus 2.6x, and this y-intercept b0 equals to 0.2. So when x equals to 0, the expected value of y is 0.2. That's the interpretation for the y-intercept. Now for the slope, b1 is 2.6, which is positive. So for 1 unit increase in y, we can expect an increase of 2.6 units in the value of y. Now we need to find the predicted value of y when x equals to 5. So with this equation, when x occurs, we use 5, and we get y hat equal to 0.2 plus 2.6 times 5, which is 13.2. Now we want to answer the question of whether or not our regression model is a good model. To do so, we first introduce 3 important measures of variation. The first one is sum of square due to error, or SSE. It's a measure of the error in using the estimated regression equation to estimate the value of the dependent variable in the sample. Equation 14.8, sum of square due to error, or SSE, which is equal to the sum of yi minus y bar square. The next one on the list is the total sum of square, or SST. It's a measure of variation of the yi values around their mean y bar. That is, total sum of square, SST, equal to the sum of yi minus y bar square. The third one is the sum of squares due to regression, or SSR. It's a measure of variation attributable to the relationship between S and Y. And sum of squares due to regression, SSR, is equal to the sum of yi hat minus y bar square. There is a relationship among SST, SSR, and SSE, which is from equation 14.11, SST equals to SSR plus SSE. Normally, two of those three measures will be given, and you need to find the third one. For example, if SST and SSR are given, then SSE is equal to SST minus SSR. Based on those three important measures, we introduce the following two measures about the model. The first one is the coefficient of determination, and we used the notation R square or big R square to represent. It's a measure of the goodness of fit of the estimated regression equation. It can be interpreted as the proportion of the variability in the dependent variable y that is explained by the independent variable x in the estimated regression equation. And here's the equation for calculating the coefficient of determination. R squared equals to SSR over SST. And we want this value to be close to 1 to get a good model. The next measure is the standard error of estimate, and we use the notation S to represent. It's a measure. It measures how much the data vary around the regression line. It's the square root of the mean square error, or square root of MSE. And here's the equation used to compute the standard error of the estimate. S equal to the square root of SSE over M minus 2. And because this is an error term, we want this value to be small. Let's see an example. Example number 2, giving SSR equals to 66, SST equals to 88, and N equals to 22. A, we need to compute the coefficient of determination and interpret its meaning. B, we need to find the standard error of estimate S. So by using equation 14.12, this coefficient of determination is equal to SSR over SST, which is 66 over 88 is 0.75. There is 75% of the variability in Y can be explained in the variability of X, and this is an okay model since only 25% of the variability is unexplained. And the next one, we need to find S, or the standard error of estimate, which by using equation 14.16, This is the square root of SSE over n minus 2. Now, we do not have SSE, but we have SST and SSR. Using equation 14.14, SSE is equal to SST minus SSR. So, S is equal to square root of 88 minus 66 over 22 minus 2, and we get the result of 1.05. And this is the end of part 1 of chapter 14.